springs are something that exert a force. You guys have all seen a spring before. This is a spring that I have. You know, they stretch out and then they'll snap back to their previous position. Spring force. There's a formula for this called Hooke's law, so called because Robert Hooke came up with it. But that springs exert a force that is equal to minus k x or minus k delta x, depending on how it's written. I believe your textbook just says magnitude of the spring force is equal to k times magnitude of x. But either way, so this x is the displacement of the spring from equilibrium. So if I'm here, say at the end, I'm holding the one end fixed. You can't, it's off the screen, but I'm holding the one end fixed in place. This end is here, and then I go stretch it out to here. Now the force I'm exerting is the distance that the end of the spring moved. So the end of the spring is here, whereas it was here before. Whatever the distance from here to here is, that's the force. That's what we plug in for the displacement to figure out the force this spring is exerting. K, as we believe we talked about this last semester when we were doing energy, K is called the spring constant. And it is a constant for a given spring. It depends on the material the spring is made of. It's a measure of how springy it is. A larger K value means it's harder to stretch or compress the spring. The units of the spring constant. Let's think about it. Force is measured in newtons, displacement meters. So the spring constant by dimensional analysis then is measured in newtons per meter. The negative indicates that the force is in the opposite direction of the displacement. So again, if I stretch my spring, I am moving the end of it downward. That means the spring is exerting, well, not downward on your screen. That means the spring is exerting a force that is upward, back toward its equilibrium position. Upward on your, or up and down on your screen probably, or toward, if I pull toward the bottom of my page, then the force is exerted toward the top of the page. That's what that negative tells you. So if we're using Newton's second law, and we will do a couple of problems like this, the reason that your book gives the formula like this is that the negative can be confusing. This doesn't mean that when you plug it into Newton's second law, you always plug it in as a negative. Remember, when we do Newton's second law, we pick a direction to be positive, and then all forces in that direction are positive, and all forces in the opposite direction are negative. So in general, it may be better to just figure out the magnitude of the spring force and then give it a positive or negative sign based on your reasoning. And the one last thing I want to note here is that this spring and the springs that I have in my classroom, it can only stretch. It can't compress anymore because it's already compressed all the way. But springs in general can stretch or compress. Bed springs, for example, when you lie down on your bed, it sinks down. And those are springs that are compressing, and then as they compress, their displacement is downward, so they're exerting an upward force on you that is supporting your body. So let's consider a spring that's hanging. So say we have a spring, and this is where it would be. This is called the relaxed length, also known as equilibrium length of the spring. But then we hang a mass from it, and now it stretches and it's hanging down right here. Well, let's consider what forces are acting on this mass. There's one that's always there, which is gravitational. We'll assume this is on Earth, So we can use mg, even though we just got done with our unit on orbits and stuff. You can just use mg in this case. You don't need to use Newton's law of gravitation. And the spring is stretched, okay, but since it's stretched downward, it's going to exert a force upward on the mass. And so K is the spring constant of the spring. X is the distance from that equilibrium length of the spring to where the mass is now located. So then Newton's second law, let's say the mass is just hanging there, then Newton's second law, we've got Kx upward, mg downward, so they need to have opposite signs. And if it's just hanging there, it's not accelerating, so the net force is 0. So in this case then, Kx equals mg. This is an equation you're going to use several times on your homework, but it is not a law of nature or anything. This is what happens when you have a mass hanging from a spring and everything's at rest and there are no other forces. This is not a general equation that is always true. Okay, just to be clear. So we could say for example that a spring with spring constant 56 newtons per meter has a mass of 48 grams hung from it. When it comes to rest, how much will the spring have stretched from equilibrium? This is exactly like the scenario I was talking about up here. Net force is ma. We've got kx upward, mg downward. Add up to 0, so kx equals mg. So we can go ahead and just plug stuff in. K is 56. How much will the spring have stretched? So x is what we're trying to figure out. If it's vertical, you could use y instead. That would be reasonable. Mass, 48 grams, which is 0.048 kilograms. And g, of course, is 9.8 meters per second squared. 0.048 times 9.8 over 56. It's 0.0084 meters. So actually this spring would only stretch 8.4 millimeters. So it's pretty small distance. Okay. Hooke's law does give us a linear relationship between force and displacement, and this is what you're going to investigate in your lab that you're doing today. What we're going to do is, using force sensors in our new log program, we're going to measure the force that a spring exerts when it's displaced at multiple different displacements. Okay, so you're going to collect a data table. You're going to wind up with a data table of displacement, force, and you're going to have 10 values. Okay. Now notice this is displacement from equilibrium. So in practicality, when we're doing this, we need to measure the length of the spring, and then we need to measure the length of the spring once it's stretched, measure the length from end to end, and then the displacement you get by subtracting those two. So make sure you do that when you're doing your lab here. And these 10 data points you're going to plot, and you'll get some kind of scatter plot. We're just going to do the magnitude of the force, so it should be linearly increasing. So hope you'll get a scatter plot that will hopefully, kind of look like a positive linear correlation. And then you're going to draw a best fit line. And because if we graph position versus force, then force is our dependent variable. It's our y-axis. Our y-x is our independent variable. It's our horizontal axis, our x. And this is linear. So then the slope of this best fit line should be equal to the spring constant. So you're going to use that to figure out a spring constant. So one, you're going to eyeball a best fit line. You're also going to do what is called a linear regression. There are instructions for this on your sheet, but I want to just say, so show you go to Stat, Edit, and then you have these lists here, and you can type in values into your list. I have data in here. I don't know what this data is from. But once you have data in your list, you can go Stat, Calc, and go down to linreg. That's a linear regression, and it will calculate a best fit linear equation for your data. You go linreg and say I want to do L1 and L2. And I hit enter, and it gives me an equation. So this tells me that, this gives me a best fit linear equation. These two values are the values in the equation. For you, your B should be pretty close to 0, because spring force is just kx. There is no y-intercept. And then the A value would be your spring constant. If you follow the instructions in the lab report, you will turn diagnostics on before you do this, and then you'll get this value of R. R tells you how good of a correlation this is. If R is close to 1, then we can say the graph is linear. Or I should say absolute value of R is close to 1, because if it's close to -1, that means it's linear but with a downward slope. So R values can only ever be between -1 and 1. R is called the correlation coefficient. A correlation coefficient of 1 or -1 means that every one of your data points is on your best fit line. That's very unlikely to happen. But you should get an R value for this. You should get an R value that's at least bigger than 0.9, because you should get a linear result. But this is how you tell, does your data fit Hooke's law? Well, you look and you figure out this correlation coefficient. That's one way of telling whether your data fits Hooke's law. There are other ways, but that's what we're going to do. So you're going to do that, see if your spring obeys Hooke's law first, and then you're also going to look at the value and get what your spring constant, your experimental spring constant is, and then compare it on your sheet that you're going to be passed out. There is a list of the theoretical spring constants for each of the springs that you could be using. So that's what you're going to do in your laboratory investigation today. And hopefully that won't be too difficult to figure out. You're going to do all that. You're going to write a conclusion and then turn it in.